Think about the surfaces you touch every single day. Your phone, your watch, even the windows on a skyscraper. They look pretty simple, right? But underneath that smooth finish, there's this hidden world of incredible microscopic engineering. Today, we're going to pull back the curtain on the science of sputtered thin films. It's the tech that gives our everyday stuff invisible armor and, really, just stunning, durable beauty. So let's dive in and see how science is making our world stronger, cleaner, and a whole lot more colorful.
All right, here's the plan. We'll kick things off by looking at the big challenge these films are designed to solve. Then, we're going to check out 3 amazing superpowers they can give a surface: the ability to clean itself, unbelievable strength, and color that's literally built right in. And to wrap it all up, we'll look at what this all means for the future.
So, Section 1, Invisible Armor, Visible Beauty. This really gets to the heart of the problem. Forever, designers and engineers have had to make this tough choice. Do you make something that looks amazing, or do you make it strong enough to last? And that leads us to the million-dollar question, right? How can you get the best of both worlds? How do you create that perfect, sleek finish on a gadget or that brilliant color on a faucet and make sure it doesn't scratch or fade away in a year? Well, the answer, it turns out, is all about manipulating matter at the atomic level. And this is our hero technology, sputtered thin films. Just try to picture this, a super high-tech process that lays down a coating, just atoms thick, onto pretty much any material. This is not paint. It's way more like giving an object a brand new engineered skin. And this new skin, it comes with some incredible new properties, these superpowers we've been talking about. Okay, let's see this in action. Our first case study, the self-cleaning surface. For this, we're going to zoom in on a material called titanium dioxide, or TiO2 for short. And it has a truly remarkable talent. So how in the world does this work? Well, engineers don't just spray this stuff on. It's way more clever than that. By sputtering the TiO2 at a very specific angle, they create this incredible, tilted structure made of tiny columns. The best way to think about it is like a microscopic coral reef. This wild architecture massively increases the surface area, which is the whole key. It creates way more spots for photocatalysis to happen. That's a process where the surface uses light to literally break down dirt and pollutants. But wait, there's another crucial step. When the film is first put down, its atoms are all jumbled up, and its self-cleaning power is pretty low. But then you heat it up to around 550 degrees Celsius, and a total transformation happens. The atoms snap into this highly active crystalline structure. This doesn't just supercharge its cleaning ability, it also makes the surface clearer and glossier. You are literally baking in both the function and the beauty at the same time. And the level of control here is just astounding. By just tweaking the gas pressure during the sputtering process, you can change the film's density. A higher pressure makes the film more porous, which changes how it reflects light. This means engineers can dial in the exact finish they want, from a super slick high gloss to a really sophisticated matte look. Okay, so we've gone from self-cleaning surfaces to our next superpower, incredible strength. This brings us to Section 3, building strength in layers, using something called nanolaminates. To build a super resilient surface, you start with ingredient number 1. A material like aluminum oxide is ridiculously hard, which is awesome for fighting off scratches. But like a lot of super hard things, it has a weakness. It can be pretty brittle. So you bring in a partner. A material like zirconium oxide is tougher, more flexible. It provides the resilience that first layer is missing. You see, on their own, each one has a major drawback. But when you layer them together in this alternating nanoscale pattern, think of it like a microscopic lasagna of strength. Something amazing happens. The boundaries between the layers actually work to deflect any cracks that form, stopping them in their tracks. This combo becomes way more resilient than either material could ever be on its own. It's why these coatings are perfect for really high-stress jobs, like on biomedical implants or tough electronics. All right, now for our third and final superpower, and I gotta say, this one is my favorite. Creating vibrant, amazing color without using any paint or pigment whatsoever. This is Section 4, where we get into the magic of what are called transition metal nitrides. This is so cool. The color you see here doesn't come from a dye. It comes from the actual physical properties of the material and how it messes with light. By picking the right recipe of elements, you can create a whole palette. Titanium nitride, you get a beautiful rich gold. Chromium nitride gives you a sleek silver gray. And if you start mixing them, like with titanium aluminum nitride, you can get these deep violets and blues. It's incredible. And remember, this is not just about looking good. These coatings are also insanely hard. Just to give you some context, a diamond is around 100 gigapascals or GPa. These materials are a big fraction of that. And just look at titanium vanadium nitride, TVN. It's clocking in at over 31 GPa. That is a massive amount of durability fused right into the color itself. So why does this matter so much? Well, it means that the gold finish on your watch or the deep blue on your phone case isn't just a thin layer of paint that's going to scratch off. The color is the armor. It's a fundamental part of the surface, making it beautiful and incredibly long-lasting. So all of this brings us to our conclusion. The future of surfaces. When you put all these pieces together, self-cleaning, super hardness, built-in color, you start to realize we are really at the beginning of a whole new era in material science. I think this quote just says it all perfectly. We are fundamentally changing our relationship with the materials that make up our world. We're not just shaping objects anymore. We are actually programming their outermost layers to do these incredible new things. So what's the big takeaway here? First, that this microscopic engineering is giving everyday surfaces amazing new abilities. Second, we can now control both function, like self-cleaning and hardness, and looks, like texture and color, with insane precision. And finally, the result is a new generation of products that don't make us choose between beautiful and tough. We can, finally, have both. And that leaves us with one last kind of fascinating thought. We've seen surfaces that can clean themselves, protect themselves, and even color themselves. The possibilities this opens up are just mind-boggling. So I'll leave you with this question. If this is what we can do today, what on earth are we going to teach the surfaces of tomorrow to do?